Good morning, colleagues and postgraduate students. Good morning also to you, Ms. Makanye. Thank you for your assistance in the background. As it has been indicated today, our workshop is on T-tests. It's on Anova and Ancova. So basically, we'll be focusing on tests that are around the mean. So we will be looking at statistical tests that aim to when we are doing analysis that is around the mean, as I've said. So as usual, I'll just try to run through some concepts. Most of the concepts have been covered in previous workshops, so I'm really going to rush through those parts so that we can have a sufficient time to cover the actual tests. So as a foundation, when we do a study, this is where we'll start. We know that as a researcher, your problem occurs within a population. So whenever you do a study, what you want to measure or investigate is within a population, right? It's important to always have that mind that what you are investigating is within a population, and you will define what constitutes the population by giving the inclusion, the exclusion criteria. And then based on that definition, we will be able to say this is the population size, which will be all the units that meet that criteria that you would have specified. Their population is often large, such that we are not able to measure all the units within their population. And we also know that we can use a sample to estimate what is occurring within a population. So if we select an adequate sample, it's not always necessary to actually measure the entire population. So we then have a sample that we deal with. So the sample is our means to the population. The interest is in the population, but then we use the sample to get to the population. Because our interest is in the population, once we've measured attributes within the sample, then we want to go back to the population. How we get back to the population is through inferences, meaning we want to take what we see from the sample and we want to do what? Paste it on the population. In other words, we can say we want to generalize, or we say we want to make inferences. So that's where the concept of inferential statistics comes in, is that you have a sample, but then you want to take what you are seeing from the sample and you want to make inferences or generalization about the population, since your interest is in the population, not the sample. So the sample will then be a subset of the population. And if you do not take a sample, then we say you have a census. The sample size will depend on the estimation. So as I've said, the interest is in making inferences about the population. So we test hypotheses about values of population parameters. I will explain population parameters. Or we predict and estimate values of population parameters, and we make decisions based on sample statistics. I will come to that. So what we measure, the things that are occurring within a population, we say they are parameters. So if I compute an average from the population, I will say it is a population average will be a parameter. It is fixed because the units, once you've defined the population, the units will be fixed. As in, if the population has 500,000 units, it's got 500,000 units. for as long as your inclusion and exclusion criteria doesn't change. What is included, what is excluded will be the same, which means that if you had the opportunity to actually measure all the units within your population, you would get you'll get a fixed value, meaning that even if you measure it again tomorrow, it's still going to be the same value, because what constitutes the population, it doesn't change. So if you were to measure it will be the value. That's why we say it is fixed. However, because of the size of the population, it's not always possible to do what? To measure all the units within the population. But in the real sense, the value is fixed, because what constitutes the population, as I've said, doesn't change, such that if you really had the resources to measure, you'll get the same value each time you measured. Obviously, assuming that yeah, you are not measuring, let's say, age, such that you measure it this year, and when you measure next year, it changes because the people have, there's an added year in terms of if you are using age as an example. But in general, what you are measuring would be fixed. On the other hand, we talk about statistics. These are things that we measure from the sample. So everything that we measure from a sample will be referred to as sample statistic. And we use them to do what? To estimate population parameters. So as I've said, we are interested in the population, meaning we are interested in population parameters, but we use the sample to estimate the population parameters. I think this also, as I always say, it's important that you have this background. It will assist you. When you see parameter, the word parameter being used in statistic, you will always know that it's talking about the population. It's a value of the population. When it's talking about a statistic, it's talking about something that has been measured from the sample. So these are examples. As I've said, you can have the population mean. So if I'm measuring an average, and I'm measuring from all the population units, that's going to be population mean. I can have the population standard deviation. Sometimes maybe I'm interested in the proportion, which can be the proportion of teenagers who smoke in the population. So if I'm able to measure all the teenagers within the population, then I would be able to get a proportion, which would be a percentage of the teenagers who smoke. I can also have a correlation. And then on the other hand, then I have the statistic that I used to estimate the respective parameters. So if I am talking about the population mean, I can estimate it using the sample mean. The sample mean will be a statistic. And similarly, the other ones that have been listed there, they would be your statistics. So we have, as I've said, we estimate, we use the statistics to estimate population parameters. So the sample statistic is used to estimate the population parameter, and we say it's an estimator. That sample statistic that is used, we call it an estimator. Then that particular, the value that would have estimated, we say it's an estimate. So once I have the sample mean, that sample mean is what is an estimate of a parameter. And then one value that is used as an estimate of a population parameter is referred to as a point estimate. Sometimes the estimate can be an interval. Sometimes it's a point estimate. So it's important now, when you know that I'm interested in the population, but I'm using the sample, it's important to know that a sample, it's not the same as a population, such that when you sample, you can get different samples. So if I sample, I follow the same process. I sample from a list of grade 1 learners. Let's say I sample randomly. And if another person comes and they sample, we're not going to get the same samples. So that background knowledge is important because it then says that what you get as the statistics or the estimates that you get will differ from sample to sample. So when we repeat the experiment from the same population, we will get different results. Usually we say most of the time we'll talk about probability sampling and probability sampling because there is a link between probability sampling and in inferential statistic. So when you are not able to use probability sampling, you might lose some of the theoretical properties that are required for sound inferences. So it doesn't mean that you can't make inferences. It just means that you just have to be careful as to what extent you can make inferences. And you just have to be aware of the bias that can be introduced in your sampling and be able to minimize it. So a typical example is if you are going to be doing something maybe about brands, maybe you're looking at dishwashers, right? And you are studying something around that, and let's say you can't do a probability sampling, so meaning you're gonna do a non-probability sampling approach, and you decide that you're going to target people as they do their shopping. Maybe you stand next to yeah a shop in a mall. It would be important as when you go. If you go at certain times, you might be likely to find certain groups of people. So if you go in the morning during the week, you're gonna find people who are not employed, or maybe they're self-employed, but your regular person at that time would be at work. So that can introduce bias in that way, in the sense that you might just find a certain group. So your sample is now biased. So it's always important to be aware of your population and be aware of the bias that can be introduced at sampling and try to minimize it so that when you make inferences, at least you can, even as you describe how you sampled, you can also outline how you tried to minimize certain biases. When you're doing probability sampling, you can actually even measure the bias, and you can correct for bias, but that can only be done for probability sampling. With non-probability sampling, it's just an awareness and trying to minimize it to the best that you can. So we make inferences, as I say, from the sample. So it's important, as I say, that your sampling is sound and you try to minimize bias. So I'm going to move on to the sampling distribution, which is something that is important to understand when you are doing inferential statistics, because statistical tests that are done rely on sampling distribution. So a sampling distribution is a theoretical distribution. So you can see by the definition, it's a theoretical. It means that as someone who is collecting data, doing analysis, those distribution have already been established. So it has already been established theoretically that this is the sampling distribution of the mean. So when you do analysis, you tap onto that, onto what has been established theoretically. So it's a theoretical distribution of all the possible values of some sample statistics that would occur if we were to draw all some possible samples of a fixed from a given population. So If we were to draw all possible values of some sample statistic, remember sample statistic talks about the sample. So if, for example, we use the sample mean as our sample statistic, we say the sampling distribution, it's all the possible values. So it's all the possible averages or sample means that we would get if we were to draw possible samples. So if we have a population and I draw a sample maybe of size 50, and I compute the sample mean, and then I go back to the population, I draw again a sample of 50 because it's the example that is used there, it's a fixed size. I draw 50 and then I get a sample mean again. I draw again, I get a sample mean. The distribution of those sample means, that is what we call a sampling distribution. And it's a frame that we use for statistical decision making. So every statistic, when we are doing inferential statistics, we are going to come across statistics, because if I am interested in the mean, because I'm using a sample, I'm going to be working with the sample mean. If I am doing a study and it's about a prevalence, because I'm drawing a sample, I'm going to be working with the sample proportion, which I will be using to make decisions about the population. So this is just a visual description of what I tried to explain. So you have a population, it's got a size, and it's got a standard deviation, it's got a mean. So if we assume x1, x2, x3 are the averages, so meaning I go to this population, I select a sample of size n, and then I get an average from that sample. Let's say I take the population of postgraduate students at UNISA. I sample 100, and then I compute their age, the average age. So x1 will be sample 1, and x1 bar will be the sample average for that sample. I go back again to the population. I select another sample. Then I also compute an average, which would be the average age, because I'm using age as an example. Then that is going to be x2. I go back to the population again. I select another sample. So, and I do it repeatedly. Here I'm only showing 3 points because I'm showing that I would have sampled 3 times. I can be able to plot those averages. We expect those averages to be bell-shaped. So the red is supposed to be bell-shaped. That is my bell-shaped. So this, if I do it repeatedly, it's going to give me the sampling distribution of the mean, because I'm doing the mean. As I say here, I'm only showing 3 sample averages. If I do it repeatedly, I'm gonna have these all over, but they're gonna take the shape of a bell shape. So this is another example. So if I have 6 scores, here are the 6 scores. You can see them 1, 2, 3, 3, 4, 5. And then if I compute the mean, if you can go and check, the mean is 3. If I select 2 scores at random, so I select the first score, I select the second score of size 2, meaning I'm selecting 2. For example, I can, first selection, I can get a 4, and then second selection, get a 3. That the sample mean for those will be 3.5. If I continue that way, I have this possibility such that first I can select a 1, and then when I select again, I can get a 1, or I can get a 1 and a 2. A 1 and a 3, a 1 and a 3 again, because I have got 2 3s in that in the population. Inside, you are able to see if I get a 1 and a 1, the average is going to be 1. If it's a 1 and a 3, the average will be 1.5. So here I have all the possible sample means that I can get. And we know that the population mean, because remember here with this example, the population is these 6 scores. This is the population. Then the average of this would give me the population mean. These are the sample averages. What you see here. So here, all of these are the possible sample averages, depending on the combination of the scores that I would have selected. And I can be able to compute the probability now and say, what is the probability that my sample mean will be 1? I only have one occurrence where the sample mean is 1. So it's going to be 1 out of 36, because all of this, they are 36. And then I can look at what's the probability that the sample mean will be 1.5. I've got 2 occurrences, can only occur 2 times, here and here. Then it's 2 divided by all there. So here, obviously, to compute the probability, I'm tapping into what we've covered before, that when you compute a probability, we look at the event of interest divided by all the possible events. So here, the event of interest is that I get an average of 1.5. Those events, they occur 2 times. And then how many events do I have in total? I have 36. So it's going to be 2 out of 36. That's how I get the probability. For me to get a sample mean of 2, how many of them do I have? I've got 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Yes. So I've got 4 possible outcomes where I can have an average of 2. So that's going to be the ones that are favorable to what I'm interested in. It's 5. That's why it's 5. And then all the possible events, they are 36. So you can continue in that way and be able to compute the probability of getting each of these possible means. And then I can be able to get the probability. And then I can be able to plot it. So that would give me the sampling distribution. So this is the sampling distribution of the mean on samples of size 2, right? From a population of what? Of 6 scores. So this is the sampling, and then in the middle here, these ones in the middle have a higher probability. And you can see as you plot it, it's symmetric. So here I'm using this so that you can have a visual, a picture of what we mean by sampling distribution. So using this small data, you can see that if you sample repeatedly, here I've fixed the sample size to be 2, and now we're using the sample mean. You are able to get the sampling distribution from a population of 6. So this gives you a picture of, theoretically, when we say these things have been established theoretically, we already know that when you have a sample mean and you sample you sample from it many times, this is what we expect. And then that's what it's used for when we do inferential statistics. So the last example is the one where it's using a coin. So if you toss a coin 3 times, So if we look at our interest being the probability of, if I toss a fair coin 3 times, these are the possible combinations. I can either get a head, and a head. Remember, it's 3 tosses. Or the first toss can be a head, the second one can be a head, and the last one can be a tail. Or the first one can be a head, and the last 2 can be a tail and a tail. Or I can have a head, tail, head, or I can have all of them being tails, or I can have 2 tails, the first, second, the last one. So these are the possible. I hope you can see how we get to this. But now I'm interested in obtaining 2 heads. So I have to look at this, the possible outcomes, and see how many of them actually talk to my preferred outcome, which is now I am focusing on getting 2 heads. So I can get 2 heads if I get a head in the first toss, the second toss, and the last one is a tail. Or if I get a head, a tail, and a head. Or if I get a tail, a head, and a head. So the 3 outcomes here out of this 8 give me what they give me the 2 heads. So the probability of getting 2 heads is going to be 3 out of 8, right? Because the ones that are favorable, it's 3 of them, and then you say you divide by all possible outcomes. All possible outcomes, I have 8 of them, which is this probability that I get here. We can also compute the probability of getting 0 heads. What's the probability that I get 0 heads? What's the probability that I get 1 head? What's the probability that I get 3 heads? I can compute all those outcomes of the probability for those outcomes of interest. And you can see the probability that I get 3 heads, it's only, I only have it once. One outcome here gives me 3 heads. So it's going to be 1 out of total, which is 8. And then the probability that I get 1 head, I can also check how many of these outcomes are giving me a 1 head, and then it's 3 of them. And then 0 heads, it's 1 of them where I have everything as tails. So I hope you can see how we got to the probabilities. And similarly, you can now also plot that, and you can be able to get a sampling distribution. So this is how sampling distributions are obtained. So in general, if we look at 10 coin tosses, I used 3. If we look at 10 coin tosses, we can see if the focus is the number of heads, we can plot the probability of getting 0 heads, 1 head, 3, 4, and so on. And we can see that on the left, as I've said, you have those unlikely outcomes, that those unlikely outcomes will be those probability of getting 0, the probability of getting 1 head, or the probability of getting everything being, all 10 of those choices being heads, which is 10, or 9 of them being heads, which is this probability will be here. And you can see here in the middle, the 4, the 5, the 6 in the middle, they have higher probabilities. So this is another visual illustration of the sampling distribution using small data so that you can have a picture. But then these properties, as you can see, you start to see with the sample mean that we expect that on your left, your extremes, you will have those unlikely outcomes, and then in the middle you have those outcomes that have higher probabilities. So this trend is what is used. These theoretical things that you are starting to pick up as I'm going through the examples, it's what is used in inferential statistics, that when we talk about the sample mean, we expect that when we do the distribution of the sample mean, On the extremes, you have those unlikely sample means, and then in the middle, you'll have those with high probabilities. So we can determine the sampling distribution of different sample quantities, right, from the data of a random sample. And these quantities, we refer to them as sample statistics. We've looked at standard deviation, the variance. The quantities such as the sample mean, some are usually used as estimates. I think I've mentioned this at the beginning, that the sample means what we get from the sample. We use them to estimate what population parameters. But now theoretically, we know the sampling distribution of these quantities, because I used a small example to just give you a picture. So they have been investigated theoretically to say when we have a sample mean, we expect the sampling distribution to be like this. And that's what we use in inferential statistic. When we talk about the mean, yes, we know that the value will depend on the sample that is selected. And the sample mean is a random variable. So it's got a probability distribution. I think I showed the probability. We're able to look at the probability of, this was the sample mean example. Here is the distribution. So our knowledge about the distribution of the sample mean enabled us to determine how well X bar can be used as an estimate. So because we know certain attributes about the sample mean, this enables us to now check how well a certain X bar can be used to estimate its population. So sample statistics, or the sampling distribution of a sample statistic, is the main way to determine how good of an estimate a sample statistic is. So because we know the expected sampling distribution, then we use it to determine an estimate that is from a sample that we have now, that we are using in the study. We use it and we compare it against the expected sampling distribution. And then we use the different sample statistics and their sampling distribution to make a probabilistic conclusion about statistical hypotheses. So statistical hypotheses are about population parameters. So I hypothesize that the population average is this, but then I now use a sample. So meaning I'm going to end up with a sample statistic. And then I have to be using its sampling distribution to make probabilistic conclusions about the claims that I'm making, which are the hypotheses. Yeah. So that most statistical analysis, it's based on calculation of the sample statistic, right? We will calculate the sample statistic, which will be, if we are interested in the population average, it means that from our sample, we'll compute the population mean. And then we can compute the sampling distribution, and using the sampling distribution, we can make inferences. So when we are doing hypothesis testing, we compute test statistics, which I will show when we start to do examples. Sample data is used for calculations, and it gives us a single number. So you have your sample data. If we talk about the mean, you compute an average, and then you compute a test statistic, which will be a single number. And you compare that to the null hypothesis. So these are examples of our test statistic when we have z-scores, t-values. I think you've come across this. We will talk about the t-value. We'll talk about f-values. So this sampling distribution for this test statistics, when the null hypothesis is true, are known. So that's what I've been trying to say, that theoretically, the sampling distribution for these statistics when the null hypothesis is true are known. So their sampling distributions when the null hypothesis is true are known, which is our point of reference. Yeah, and we also know also from statistical theory that there is this theory. But what I want you to get from the theory is that we know that in a lot of tests that we do, there is always the assumption that is brought in, which is the assumption that there is symmetry, or the variable is normally distributed, or it's bell-shaped. Yes. How it comes in, it's because according to this theory, it says that if you have a large sample, right? If you have a large sample, so when you have a large sample, the distribution of the random outcomes will be similar to or will be close to a normal distribution. So I think what I must also mention is here that when we say something follows a normal distribution, it means that the observed probability of each outcome when we talk about a discrete random variable, or observed probability of a reasonable set of intervals for a continuous random are well approximated by the corresponding probability of some name distribution. Okay, maybe this will explain it better. So if you look at the red being the original distribution, the central limit theorem tells us that when the sample is large, even though the original distribution might not be normally distributed, but when the sample is large and we collect the mean of those values repeatedly, we will have a normal distribution. So when we have large data, because especially when we work with things around the mean, there is always this assumption about symmetry. What the central limit theorem tells us is that even if the original distribution was not normally distributed, but when we have a large sample, according to this theory, what we have will be approximately normal. So if we go back to the example, the scores, if let's say the population is 150 instead of 6, and we repeatedly select samples of size 40 instead of 2. Remember in the example I used 6 as the population size, 2 as the sample size. Here now I'm saying the population size is 150 and the sample size is 40. If we compute the sample means for each sample, so we go and select many samples, right, of size 40. Then according to this theorem, when we look at the distribution or the histogram of the sample means, they will show us a bell-shaped, even if the individual scores were not normally distributed. So even though the original was not normally distributed, but when we have large data, we know that the distribution of the sample means it's going to be normally distributed. This is important because, as I say, when we are doing statistical tests, we always talk about this assumption of symmetry. So this says to us that when we have large data, so also what I must say is that you use your knowledge when it comes to assumptions. You use all your different pieces of knowledge. You use them together. So this is one piece of knowledge, which is when you have large data, you can, and you know that the variable is not an extremely skewed variable. You can say the assumption of normality is upheld. And you can use this theory, as I said, together with other pieces of knowledge. So if, for instance, you have large sample, but you know that you have an extremely skewed variable. So even if you have a large sample, it wouldn't be wise to just say, because of the central limit theorem, I'm going to assume that my data is normally distributed. When you know the variable to be a very skewed variable, so even though you can have large data, you can still now treat it as a skewed variable, because you also have that piece of knowledge to say this variable is an extremely skewed variable. Always use income. When you have unequal, like in South Africa, you have a very, very unequal population. Income will be very, very skewed, such that even if your sample is large, it would not be wise when you talk about income to talk about it in terms of average, because even though the sample might be large, because the variable is still very skewed, it would be better maybe to talk about median income and use other tests that are not about the average. So this central limit theorem, we use it quite a lot, even though we don't say it, but you will hear maybe someone say, because your data is large, let's just go ahead and we can just assume that this assumption of symmetry is met. But as I say, you use it, but you use it together with other pieces of information that you know about the variable. So I think this is just a summary of what I was trying to explain. So the original population, here it is. It might not be symmetric as you see it, but when the sample is large, we say that the sampling distribution of the mean will approach normality. So such that whenever you have a large sample and you have assumptions that talk to symmetry, normality, bell-shaped, you can continue and assume them to be met, unless otherwise you know additional information about that variable, as I've used income, that yes, I might have a large sample, but I know that income is very skewed. So even though I could use this theorem to say that I can continue and do the test because the assumptions are met. But here I have to be cautious because I have an extremely skewed variable. So maybe it wouldn't be better. It would be better to really treat it as an extremely skewed variable and use other ways of summarizing it instead of using the sample mean. So I think you can see here that as the sample size is increasing, this distribution, you can see they approach symmetry. You can see here, as the sample size is increasing, the distributions, they approach symmetry. Yeah. So I'm just going to move on to hypothesis and just run through this. So we are aware that when we are doing statistical tests, we want to test hypothesis, which you can see it as a claim about one or more population of interest. So you as a researcher, you will make a claim, right, about the population, and it will be around the population parameter or relationships or just one parameter. So your claims will be about the population. Because your claims are about the population, your claims will talk to population parameters. So here we can say, we can make a claim that the average IQ of grade 12 learners is 100, right? It's a claim that we can make. And this claim now, it's about average IQ, which is about the population mean. And then we can also maybe look at two populations, say from area A and area B. And we say the population averages in this case will be for the IQ, the variable IQ will be, we can say they are different. And I've also used prevalence. And always remember, these claims, they will be now tested against the data. So in hypothesis testing, we want to study two opposing hypotheses, which we refer to them as the null and the alternate hypothesis. The two hypotheses are mutually exclusive and they are exhaustive, so that when one is true to the exclusion of the other. So they don't overlap. We collect data, we analyze it, and we use it as evidence to decide as to which one of the two hypotheses is supported or which one is not supported. So if we were to summarize the steps in hypothesis testing, it would be we define our null hypothesis and the alternate hypothesis. So which will be related to the research question, right? So usually the alternate hypothesis is what the researcher wants to show. So you as a researcher, you will say you are picking up that there's a high prevalence of teenage pregnancy. So maybe as someone who's working at the clinic, it's what you are seeing and you want to study it formally. So as a researcher, that's actually what you want to show, that there's a high prevalence of teenage pregnancy. So that will be the alternate hypothesis. What you want to show will be the alternate hypothesis. And then the opposite of that, it's going to be your null hypothesis. So in hypothesis testing, you will define them and then you state them. And then you must select a criteria for your decision. So we will say we reject the null hypothesis, which is H0 at a particular level. So meaning that we reject the null hypothesis when the p-value is less than the alpha. And then we summarize our data. We have data. So this criteria, you just set it, right? You just set it. It's a criteria that you set, that this is, I will reject the null hypothesis when the p-value is less than the alpha. But in terms of the data that you have collected, you summarize it through the test statistic, meaning you compute the appropriate test statistic, and then you compute the p-value, you make a decision. So going back to the null hypothesis and the alternate hypothesis, null hypothesis denoted by H0. It states the assumption to be tested. So when we do statistical test, we do what? We test the null hypothesis. It's going to be about population parameter or parameters, because when we do a study, we are interested in population parameters, example, population mean. We assume that the null hypothesis is true. So when we do a statistical test, we assume the null hypothesis is true. Which means we test whether the value that is stated in the null hypothesis, how likely it is to be true. So the null hypothesis, for example, can say a parameter is equals to a certain value. So it can say the average IQ is this much. That's when it says the parameter is equals to a certain value. It can say there is no difference between two parameters, or there is no relationship between variables. The alternate hypothesis, it's now the opposite, right? I said the null hypothesis is what we are in, is what we test. The alternate hypothesis is the opposite, by stating that the true value of a population is not equals to. So the null hypothesis will say the population parameter is this much. The alternate hypothesis will say it's not equals to whatever the value, or it will say it's less than, or it will say it's greater than. The alternate hypothesis is what is considered to be wrong about the null hypothesis. As I've said, is what the researcher believes to be true. So the researcher will say the prevalence is high. The null hypothesis will be conservative. And then with our data, we hope that we can reject that conservative null hypothesis. We can see with examples. So if I toss a fair coin, I can say the null hypothesis is that the probability of getting a head and a tail, they're the same. The alternate will say they're not the same. If, for example, I test a drug that is supposed to reduce high blood pressure, in this instance, the researcher might measure the blood pressure before and after administering the new treatment. Here, the null hypothesis will say that the blood pressure before and after are the same. So, yeah, so the null hypothesis will say the blood pressure before and after, they're the same. The null hypothesis is silent. It will say they're the same. What you as a researcher wants to show is the alternate. So the alternate will say before and after, they're not the same, right? Because if before and after are not the same, you want to say this drug has had an influence on the high blood pressure, such that the high blood pressure before the person took the drug and the high blood pressure after taking the drug are different. So I think here it's important to see that the alternate hypothesis is what you as a researcher want to show, which in this example you want to show that this drug has ability to reduce high blood pressure, such that my blood pressure before and after will be different. The null hypothesis says, no, the blood pressure before and after, they're the same. Then, as we say, we use data to see if there is evidence to reject that null hypothesis, which is what you usually want, is to reject the null hypothesis, because the null hypothesis is the opposite of the alternate hypothesis. So it's not a hypothesis testing is not a formal proof, and it doesn't really prove that the hypothesis is true. It just says based on this data that we have evidence or whether to reject or not to reject the null hypothesis. As I've said, it doesn't prove or disprove. So the example we use, which is the court case, that it's evidence that is presented. So it's the data that we have, the sample data, the evidence that is presented. We make a decision based on that. So we say in a court case, we know that there is a reality and there is the evidence. The reality is the truth of whether the person has committed an offense or not. But decisions are made based on what? On the evidence presented. So if the evidence presented doesn't really mean that the person didn't commit an offense or they committed it. The evidence is just the evidence that is at hand, and the decision will be based on the evidence. And here what you need to see is that we can make mistakes, right? Based on the evidence. So when we do hypothesis testing, very important, null hypothesis is the hypothesis that is tested. That's very important, because then you will know that once you have your research questions, from your research questions, you can formulate the null hypothesis. And I think also when you know the null hypothesis, you will know that this null hypothesis is about the mean. I'm talking about an average. So I have to think about tests that talk to averages. So, and they are about population parameters, not about the sample. So when you put your, when you look at the null hypothesis, if you look at this, the null hypothesis cannot say X bar is equals to 0 because X bar talks about the sample. So the null hypothesis has to talk about mu, which is the population mean. Yeah. Null hypothesis is silent, does not favor any group. We assume H naught is true. That's how we do hypothesis testing. When we come in, we already assume that the null hypothesis is true. So if we are looking at two groups, we assume the two groups are the same because it's null. We assume they are the same, and we use probability theory to determine if we have enough evidence to reject it, right? Important that decisions in statistical testing, they are around the null hypothesis. So that's why we will ask, do we reject or do we not reject the null hypothesis? And then we will look at the evidence to say, do we reject or don't we reject the null hypothesis? So for any test, it's important to know what is the null hypothesis for that test. So we are doing the hypothesis testing, we can make mistakes, which we say they are errors, committed type 1 or type 2 error. As I've said, there is the reality of whether the person is guilty or not, but decisions will be made based on what? The evidence. So the court can say the person is guilty while they are innocent, or they can say they are innocent while they are guilty. Everything is based on the evidence. Yes, and they talk about beyond reasonable doubt. So there are two mistakes, which is a type 1, as I've said, type 2. With a type 2 error, they can decide that the defendant is guilty while they're innocent. Or they can say they're innocent while they are guilty. So these are the errors which can be committed, which if we bring it to our case, we have that if we let alpha denote the probability of committing a type 1 error, we have the following. We say alpha is the probability of committing a type 1 error. So meaning it's a probability that the judge decides that the defendant is guilty while they are innocent. For us to achieve this beyond reasonable doubt, we must have a small alpha. And then we can also have a type 2 error, which we say is B, the probability of committing a type 2 error. They decide that the defendant is innocent while they are actually guilty. So if we summarize here, they can decide they are guilty while they are innocent. That would be an incorrect conclusion. Or they are guilty while they are guilty. That's what we want. Or the judge can say they're innocent while they are in actual fact innocent, which is good, but they can say they're innocent while they are guilty. So moving to our case, we also have type 1 error is the probability. So I think it's important when you read this to see that type 1 error, it's a probability, right? It's a probability of committing a type 1 error. What is a type 1 error? It is the probability that we reject the null hypothesis when the null hypothesis is true. The null hypothesis, if, for example, we are comparing two groups, null hypothesis will say the average before the blood pressure before the treatment and the blood pressure after the treatment are the same. If we reject it when it's true, we will be actually saying that they are not the same. As I said, this we usually set it. and it's usually chosen to be 5%. So we know that 5% of the time we will make incorrect conclusions. We cannot avoid to make incorrect conclusions because our decisions are based on the evidence. But we say that we can accept an error of 5%. So we know that 5% of the time we will make incorrect decisions, meaning that there is a chance that we will reject a null hypothesis when it's actually true. Remember when we reject it, if I go back to my high blood pressure example, null hypothesis says before and after they are the same. When we reject it, we are actually saying they're not the same. And then type 2 error, we also talk about a probability. The probability of committing a type 2 error, we say it's beta. And I think in this session, I didn't mention it, but it has been mentioned in the previous sessions that probability, one of the properties we know that is between 0 and 1. When the probability is 0, it means that the likelihood of that event occurring, it's 0. And then when the probability is 1, it means that that event will occur with certainty. We are certain that it will, obviously, then the range will be, as I say, between 0 and 1. When it's closer to 1, the probability is higher. When it's closer to 0, the probability of that event occurring is lower. From the type 2 probability, which is we don't reject the null hypothesis when it's false. So when the null hypothesis says that the two treatments are the same and we don't reject it, when it's false, we are committing a type 2 error. And the complement of the type 2 error, which is 1 minus the type 2, the probability of type 2 error, is what we call a power. And then that's a probability that we reject H0 when it's false, which is what we want. We want to reject H0 when it's false. So that probability, we say it's power. You want your statistical test to have high power, enough power to reject H0 when H0 is false. I think maybe some of you do know that when we compute sample size, we will also, depending on the approach taken, other approaches use power analysis, where we say we want to have this much power. We want our statistical test to have this much power. So given that we want this amount of power and other things that we specify, what is the sample size that is required? But I think very important is that the power of a statistical test, it's a probability that it rejects, means that it finds the effect when the effect is there. So it picks up a difference when the difference is there. That's the power of a statistical test. So it's 1 minus the type 2 error. The probability that we detect a difference when it is actually present, meaning we reject the null hypothesis when it's false. The power is usually set at 0.8. So a summary, we can commute 2 errors, type 1, type 2. Type 1 is if we reject the null hypothesis when the null hypothesis is true. We don't want to reject it when it's true. We want to reject it when it's false. Remember, we say we are committing these errors because we are saying our decisions are based on evidence. And same as a court case, there is an underlying truth there as to whether a person has committed an offense or not. But decisions are made based on the evidence. So it's the same thing. If we have a treatment, we can go to, if it's not possible, but if we were to go to the entire population and give the treatment to whoever constitutes the population, would be able to get the truth of whether the treatment is effective or not. So the truth is there. We're not, but our decisions are based on what? The sample, what we have sampled. And we say we can make errors because our decisions are based on the evidence, same as the court case. Okay, so I've explained. So we came from here. Let me just, yes, here. We say here for our hypothesis testing, we need to define the null hypothesis, the alternate hypothesis. I've explained what is null, what is alternate. Spoke about that. We need to specify the criteria. When do we reject the null hypothesis? So we say we reject the null hypothesis when our p-value is less than a certain alpha. Alpha is usually selected to be 0.05. So I've explained what is alpha, which is the probability of committing a type 1 error, which the probability that we reject the null hypothesis when the null hypothesis is true. That is a type 1 error. So now we're coming to here. Yeah, we've summarized this. So we're coming to the p-value. We've talked about a type 1 error, a type 2 error. You saw in that, in the criteria, we say we reject the null hypothesis when the p-value is less than alpha. So for us to compute p-values, we tap into sampling distributions. So if you look at the right here, the picture that we have the distribution of sample means. If we use the sample mean as an example, I think you saw with the examples that I did that when you plot the sample means, this is what you get this. And we saw that on your extremes, it's where you have the low probabilities. So this would be the region where you have the low probabilities. This would be the region where you have low probabilities, and the ones here would be those ones which have high probabilities. So that has been theoretically established. So the p-value would be now the probability of observing the sample data under the assumption that the null hypothesis is true. Yes. So the p-value, it tells us the probability. What is the likelihood of observing this sample data? So we have a sample data, right? We have measured people before, and we have measured them after giving them a treatment. The null hypothesis says that the mean before treatment is the same as the mean after treatment. So the p-value would be the probability of, we have the sample, which is going to give us the sample mean before and the sample mean for after. Yes. And yes, we have the sample mean before and the sample mean after. But we have what we know about what we expect the distribution of the sample means to be under the null hypothesis. We expect the sample means to be close to H naught when the null hypothesis is true. So for example, H naught will say, if we say before and after are the same, we are actually saying the difference is 0. So we will be expecting the sample means to be close to 0 because the null hypothesis says the difference. So we'll be expecting the differences to be close to 0. So in that way, you can see the p-value as the probability of observing the sample data under the assumption that the null hypothesis is true. You can see it also as a cutoff point below which we will view the statistic from our data as not compatible with the null hypothesis. So we're going to have data, and then from the data, we're going to compute a statistic. And we want to see if this statistic, is it compatible with our null hypothesis? So we're going to have, yes, as I've said, I'll show with the next diagram. So if we use this example, if we toss a coin 100 times, the null hypothesis, if we land on a tail 50 times and head 50 times, but the coin is balanced. If the coin lands on heads 95 out of the 100 tosses, the p-value in this case will be the probability of getting 95, 96, 97, 98, because we know if I toss it, yes. Now it takes us back to the example that I used about the coin toss, to say when we were tossing it 3 times, we could plot the probability of getting 1 head, 2 heads, 3 heads, like that, or no heads. And we able to plot it. Also, if you remember the diagram that I showed when we tossed it 10 times, and we can look at the probability of getting 0 heads, 1, and we saw that on the left, on the extreme, you have those probabilities of getting 0, a 1, and then on the other extreme, you're right, it's the probabilities of getting 10, 9, 8, the other extreme. So this is the same here, that if I toss it 100 times, in the middle, I will have the probability, I will have those outcomes which will have high probabilities. And then on the extreme, the left and the right, I have those outcomes. Those outcomes on the left and the right, if you remember to the 10 courses, 10 tosses, you had your 0, your 1, those outcomes with a small probability. And then you also have the other extreme of having everything as heads or 99 as heads. That would be the p-value, those extremes. Important, yeah, we use the p-value when we do statistical test. So if you look at this, it says you must be greater than 0.05 because I failed to reject you. So it goes back to our criteria, that we set a criteria to say we reject the null hypothesis when the p-value is less than a certain alpha, which alpha is 0, is usually set at 0.05. Statistical tests, we do them to provide evidence. It is a prescribed way that we compare our observed data against a claim. So there is a claim that we make about the population, and then we take our data. We compare the data against that claim. Hypotheses are about a population parameter, important. So our results, they are captured as probability. It quantifies the extent to which the observed data agrees with the hypothesis. Yes, we want to see the hypothesis will be the null hypothesis. We want to see the extent to which this data that we have observed agrees with the null hypothesis. So after this, we can take a break, and then when we come back, I'm going to start with the examples. So this is just a summary that if the decision is we do not reject the null hypothesis, it doesn't mean the null hypothesis is true, because we know we can commit errors, right? When the decision is do not reject the null hypothesis, it doesn't necessarily mean that the null hypothesis is true. It is possible that we are committing a type 2 error, meaning we are not rejecting it when it is false. So it's important, these things are important, so that you always have a context that when we say do not reject the null hypothesis, it doesn't necessarily mean that it's true. We could be committing a type 2 error, right? The decision actually means that the observed data are consistent with the null hypothesis, but the null hypothesis might not be true. And if we get the actual full data or data for the entire population. When we have small p-values, they show a stronger support against the null hypothesis. So when we have a small p-value, we will reject the null hypothesis. However, a large p-value can also be because the null hypothesis is true. There are two things. It could be the null hypothesis is true, or it could be our test is not able to reject the null hypothesis, even if it's false. Sometimes it could be we don't have enough sample, or we could be committing errors. So the p-value, you shouldn't see the p-value as the probability that the null hypothesis is true, right? You also shouldn't see it as the probability that the alternate hypothesis is false. Because as we say, we can be committing errors. A p-value that is less than the level of significance, also a point of emphasis, does not mean that the results are scientifically or clinically significant. So also important that we do statistical tests, and maybe a statistical test will say the results will say that we have a small p-value, then we such that we do what? We reject the null hypothesis. But it doesn't mean that the statistical difference does not necessarily mean that it is scientifically significant. So the difference might not be big enough to make a difference clinically. So if the high blood pressure, if there's a difference of 2 units, if I can say, or 5 units, it will depend now as to whether clinically, if my high blood pressure is reduced by 5 units, 2 units, does it make a difference in terms of my quality of life? Or does the difference has to be above a certain threshold for you to start seeing a difference in you, so such that it's now clinically significant? And it's important to always also go back to that and then also look at the effect size, which is also what we use to look at scientific significance. I'm going to pause here. So as I said before we went on the break, the first part was really to lay a foundation and try to some concepts that are used when we do hypothesis testing. And then in this last part, we will focus on a statistical test now. Specifically, we will look at tests that are around the mean. So as I've said, we won't do the chi-square test, but we'll do everything else here. So this really summarizes the test. So we will have a one sample t-test. One sample t-test is when we have one quantitative outcome. We know that with our variables, we need to be aware of the scale of measurement. We've discussed this in several workshops. So at this point, it is assumed that you actually understand what it means when we say the variable is quantitative, meaning it's numerical. So if our around numeric variable, then we can have a one sample t-test. So there won't be a need for an independent variable because the hypothesis itself is about one quantitative variable. When we have two groups that we want to compare, but we are comparing them with regards to a quantitative variable, then we will do two independent sample t-tests. We assume the two groups are what? Are independent. So we have a categorical variable that has two levels. For example, you have yes and no, right? That is 2 levels. And then you would come that you want to compare those who said yes and those who said no. Maybe those who smoke and those who don't smoke. And you want to compare them with regards to a measured a quantitative variable. You can also have a quantitative variable and one categorical variable, but where the levels of the categorical variables are dependent. So this would be the example where you have pre and post, right? Pre is one, you have measurement for pre, you also have measurement for post-treatment. So those will be 2 levels. But because the people that you measured pre, before you administer the treatment, are the same people that you measure after, then they are dependent. Also, sometimes maybe they will measure your left foot and your right with regard to something. So because they both belong to the same person, they would be dependent. So they may probably measure the same thing on my left foot and my right foot. Maybe they compare. That would be 2 groups. You have data for my left foot. It's one level left, the other level is right, and then you compare. And then we also have a case we still have an outcome, and we have one categorical variable, or we have more than one categorical variable, but the levels are, you've got more than 2 levels. So if you go back, you have a group of people that you give a treatment, right? So others, they get exercise, others get a diet, others, they continue, meaning they don't get any treatment. So there you've got 3 levels. So then you can use a t-test, you would use an Anova. And then if you have more than one categorical variable, so if I use my example and I change it, I have 2. So I give you an eating plan, and I also give you an exercise plan. So there are 2 treatments there. There are 2 things. One is I put you in this eating plan. I also put you in this exercise plan. And then I will others do another exercise plan. So I have an exercise plan as one factor, a diet program as another factor. So in that case, I would be having more than 2 categorical variables, right? Then I also have an Ancova where I will have one categorical variable. It can have 2 levels, more than 2 levels, and then I have one. So it's important here to just see when we talk of Ancova and we talk covariates, the covariates would be quantitative. They would be quantitative. I mentioned when I was talking about hypothesis that there are, so you have your null hypothesis and you have your alternate hypothesis. So your alternate hypothesis, you can phrase it as 2-tailed or as 1-tailed. So if it's 2-tailed, if I say that the prevalence is this much as my null hypothesis, my alternate hypothesis will say if it's 2-tailed, it will say it's not equals to what I have hypothesized, right? And then if it's 1-tailed, I will say it's above or it is less. It's one of the 2. So when it's 1-tailed, it's going to have a direction. When it's two-tailed, there's no direction. If I say before and after as my null hypothesis, they are the same. Before treatment and after treatment, they are the same. The alternate hypothesis, when it's two-tailed, it's going to be their difference is not equals to 0. But if I'm doing a one-tailed test, the alternate hypothesis will say after treatment maybe is greater than before treatment, or after treatment it's lower. Maybe if it's high blood pressure, I will say the average blood pressure after treatment maybe it's lower. So just the caution is usually we do two-tailed, because two-tailed just looks at whether it's not the same. So it looks at both directions, whether it's not the same, meaning whether it's less, whether it's more. If you're doing one-tailed, the test only tests the direction that you've specified, and the rejection, the decision will be based only on the direction that you've specified. So you only do it when you really maybe have done prior tests, and you really have evidence that you should do a one-sided test, meaning your alternate will either say it's greater, it's less than. So coming back to our t-tests, with a t-test, as I've said, we're comparing a mean of a population. So important, it's about the population. The variable would be numeric. So if you look at the null hypothesis, I've said you will say the population average is equal to a certain hypothesized field. So my example was not about the population average, but was about the population proportion. And it was saying the population was what is normal, which is the mu naught. So this is the population. So this will be the population. You are hypothesizing that the population is this. So if, for example, you talk about IQ, and you are studying IQ maybe of your grade 1 learners, and maybe you are suspecting that there is something that is influencing their IQ. Maybe you suspect that it's below what is average for children in those age groups. Then you will hypothesize that the population average is this, whatever is normal, as I say. Then the alternate, when it's two-sided, it's going to tell us now to say it's not normal. So the alternate will say the population average for these children is not mu naught, where mu naught is normal. It's going to be one of these two. The assumption is our data is normally distributed. So I spoke about test statistic. So I said that when we are doing hypothesis testing, you will state your null hypothesis, your alternate hypothesis. Your alternate hypothesis will be what you actually want to show, that the IQ for these children is not normal. That will be your alternate hypothesis, because mu naught would be what you consider to be normal, what theoretically is known to be normal, right? And then the null hypothesis will say it is normal. And then we have data. From that data, we will set the criteria. When do we check the null hypothesis? We will say our level of significance, which is the probability of committing a type 1 error, the alpha. We usually set it at 0.05. And then from our data, I spoke about that, we will use our data and compute one figure. That figure, for example, for one sample t-test, it's going to be this one sample t-test. So hypothesized, you have what you are computing now from your sample, which is the X bar, and you now have there also the sample standard deviation. We know the sample variance is this, and then we have the N. So we tap into now our theory about distributions. We will now compute this the test statistic, and we know that from literature it's going to follow a t distribution with these degrees of freedom, n-1 degrees of freedom. So you will pick it up here that we use the degrees of freedom, and we usually divide by them here. When we do the sample variance, we don't divide by n, but we divide by n-1, which is the degrees of freedom. We'll try to explain the degrees of freedom as I continue. So what is important here is you have a test statistic. So from your data, you are able to use the data to compute this value, the test statistic, which is known to follow this distribution. And for instance, here, if the sample mean and what we've hypothesized is 0, they're the same, this is going to be 0, which is what is explained here. So our null hypothesis says the population average is normal, right? What we have hypothesized to be normal. So you can see here when what we are estimating from the sample mean is the same as what we've hypothesized. The numerator will be 0. The top part will be 0. And the t is going to also be 0. When the average from the sample is more than the hypothesized value, then we know the t will be greater. And then similarly, when it is smaller, it's going to be less. So what we can see is as the sample mean moves away from the hypothesized population mean, the test statistics also moves away from 0. So if when this null hypothesis is 0, this is going to be close to 0, right? Or it will be 0. So when this the x bar is close to mu naught, this value is going to be close to 0. But when the x bar moves away from the hypothesized, which is the mu naught, then the test statistic, this value will also move away from 0. So the t distribution, it is some kind of a normal distribution. Normal distribution, by now we know that it is bell shaped. When we have small samples, the t distribution is some kind of a normal distribution that is used for small samples. When we have a normal distribution and we plot it, we have what? A bell shape, meaning that most of the observations are close to the mean and few are at the tails. So when we say something is normally distributed, we are saying that most of the observations are close to the mean. We expect most of the observations to be close to the mean, meaning to be around the middle. And then we expect few observations on the extremes, meaning the tails away from the mean. Yes. We use the t distribution when our data is approximately normally distributed, but the population variance is unknown. And then we use our degrees of freedom to estimate the population variance for a t distribution. So just before I move on with the t distribution, I just want to go back to the degrees of freedom. So I said that, for example, that t statistic, the t that I showed, will follow a t distribution, which will be characterized by the degrees of freedom, which is n-1. Why, for example, is it n-1 in this case? So we use this as an example. That let's suppose we have 5 observations and their average, for example. So let's say these are the first observations. 33, 22, 30, 60, 55. If you compute the mean here, the mean is 40. And it is 40. The sum is, I think it's 200. Yes. When I sum them, I get 200, and I divide by n, which is 5, I get 40. So with these observations, if I keep this 40, let's say I say this 40 is the population mean, and I hold it constant, I can change these observations, these 5 observations, I can change them such that I still get an average of 40. However, I cannot change all of them. I don't have room to change all of them. I can change this one. It can be any number. I can change it to any number, because these other ones, I will ensure that they are not, yes. And I can also change this one to be any number, this one, and so on. All these 4, I can change them, but only one number cannot be changed, because that the last number will have to be a value that will ensure that I still get 40. So that's what we mean, that here you can change n minus 1 of the observations. You can, those ones you can vary them, but there is one observation that you cannot vary. So that's why we say the degrees of freedom will be n minus 1. So we can vary n minus 1 values. So that's why our degrees of freedom will now be n minus 1. That's how, for one group, this is how we get our degrees of freedom. Here it's one group. I have there's one statistic, which is the sample mean, and then if I'm computing the standard deviation, there is one statistic there which is inside, which is the sample mean, and then obviously you subtract the observations, and then, as I say, we divide by n minus 1, because in that I can vary everything except one of the values. So coming back, so as I've said, the T distribution is characterized by the degrees of freedom. So you can see here that when the sample size is bigger, the T distribution approaches a normal distribution. And then here, when the sample size is smaller, because to get the degrees of freedom, you use the sample size, right? It's n minus 1. You use the sample size. So the degrees of freedom, they characterize the shape, but influenced by the sample size, because to get the degrees of freedom, you say n minus 1. So you can see here, when the sample is smaller, you have it deviates more from the normal, and then as the sample size increases, it approaches a normal distribution. That's what you are to see with the first diagram. And then with the T distribution, it is about averages, right? It's about the sample mean. So if you remember from the example that I used about the 10 coins, and we were talking about if the interest is heads, we here in the middle, if the null hypothesis says the coin that we are tossing is balanced, we expect that most of the observations are going to be here. And then we're going to have a few observations here. So we will look at our sample, with our sample data, we look at whether does what we get agree with what we expect under the null hypothesis. And then the null hypothesis, we expect most of your observations to be in the middle and very few to be on the tails. So this the red we say is the rejection area, which will be the p-value. You want this to be small. Those extremes, if you saw with the when we're tossing the 10, the coin 10 times, very few observations are here. They are here when the coin is balanced under the null hypothesis that the probability for the heads to get to get an equal number of heads and tails. Here you had those extremes. So this is the rejection area, which is the p-value area. We expect it to be small if the null hypothesis is true. I go back to the example that was saying the null hypothesis was saying the coin it's not biased. All right, so it's the same here. If we come here we talk about the average, which is means. So we will expect that if you'll have a small p-value. The what is occurring here will be small observations here or small population averages here if the null hypothesis is true. The null hypothesis is true, most of our things will be here, because if the null hypothesis says that the two populations are the same, we expect a difference of 0, for example. And with a difference of 0, most of the observations have to be here. And then the other ones which do not conform will be, a small portion should be here. Once we have a big portion here, meaning the p-value, this area that is red pinkish is bigger. Once this area gets bigger, then it's deviating from what we expect when the null hypothesis is true. That's why we say we're looking for a small p-value, which is this area, meaning that this what is on the extreme is very small. Most of what we're observing conforms to what we expect under the null hypothesis. So when this area gets bigger, it means we have a lot of observations that are on the extreme, which are deviating from what we expect when the null hypothesis is true. So that's why this would be your rejection area. You look at this, the quantity. So this, what we also know is this whole area, it adds up to 1, right? And then because it quantifies a probability, it will add up to 1. This one will be the probability, will be the p-value, which will be where we reject the null hypothesis. We want this area, as I've said, to be small. I hope it makes sense. It is symmetric, right? That's also what you need to see, that it's symmetric, meaning the left and the right, they are identical. So that's why you have one standard deviation away from the average, one standard deviation in the positive direction, in the negative direction. So the two areas will be the same. So with two-tailed, we look at this plus this, then they give us our rejection area. And then I think, I've covered the degrees of freedom. That, for example, here we are doing a t-test for a one sample. It is characterized by the degrees of freedom. The degrees of freedom is n-1, so it is characterized by the sample size. As the sample size gets bigger, it becomes more normal. With small sample size, it will be a t-distribution. Obviously, it does still look bell-shaped, but it becomes more normal as the sample size increases, because when the sample is small, you can see that the tails here, they are fatter than the one that we expect for a normal. The red one, the black one is a normal distribution, which is when we have a large sample size. But when we have a small samples, you can see that the tails are fatter. So if we use an example, so if we believe that smoking affects the birth weight of newborn babies, so you are a nurse, you are working at a hospital, and you are making some observations which are making you to believe that there is an effect of smoking on the newborn babies. So you do a study and you decide to collect. Now you collect secondary data from the database of the hospital so that you can formally test this claim that you are making. So as I've said, you are saying that in essence, you are saying the average birth weight of babies, you are saying it's abnormal. That's what you are saying, because you are saying these babies are being affected by smoking, the fact that their mothers are smoking. So what you are saying is the birth weight is abnormal. So you have to look at what is normal, right? So from your experience or from the literature, let's assume that we know that what is normal is 3.5. So our null hypothesis will say what? Their birth weight is normal. Then the alternate hypothesis will be what you actually want to say, that the birth weight is not normal. So you can see the alternate hypothesis says it's not normal. As I've said, the alternate hypothesis, you must think of it as what you want to show in the study, that the birth weight is not normal. You are the one who will have to establish what is normal, tapping into literature, what is known to be normal for that particular variable. The null hypothesis will say it's not normal. And then for this data, there were 10 mothers, and then compute this the sample mean. This is the sample average, right? So this is the sample average. If we go back to our test statistic, we can also compute them the sample variance like this. Yeah, I've explained the sample variance. So here I'm showing it in detail so that you can see, because this is used quite a lot. This concept is used quite a lot in statistical analysis. It's even used in regression. So it's important to see it that when we do this, if you were to just look at the deviation from the mean, we hit a challenge that when you compute these deviations like this, if you add them up, you would get a 0. They cancel each other. So that's why the squared is introduced. Here, we know that everything that we square, even if it was negative, it's going to be positive, right? So once we square, everything will be positive. These negative signs, once we square them, they'll be positive. So that this thing of when I add these ones up, they cancel each other, I'll be able to do away with it. So that's why when we are computing the sample variance, we end up looking at the deviance square, how they deviate from the mean, but the squared. Because if we just look without the squared, we wouldn't get anywhere. They would cancel each other. So that's why the squared is introduced. Because the squared is introduced, you would have to take it out once you've computed this, and you take it out by doing a square root of the S squared, such that you end up with a sample standard deviation, not a sample variance. You end up with S. Yeah. And then you come back to your T statistic. You computed the X bar, and then you compute mu naught is what we hypothesized was 3.5. Then we computed the S and then the N. And then in this case, T that we get is minus 217. So because it's symmetric, it's minus 217 on the left, minus 217 on the right, because we know that values that are closer to 0, they support the null hypothesis, right? That's what we showed here. Values that are here, which are closer to 0, they support the null hypothesis, and values that are far from 0. So here is the t that I've computed. This will be your t. I've computed it to be this much. And then you can use so there are several ways. If you are doing your analysis in SPSS will do everything for you. You will get this, and you also get the p-value, and you'll be able to make a decision to say, with this p-value, do I reject the null hypothesis or do I not? But if you, for example, you have small data like this, and you can use your tables. You can go and check this value on the table and be able to make a decision of whether you reject or you don't reject the null hypothesis. So you can determine, we've set the alpha, which is 0.05. We know its probability of type 1 error, right? We know the type 2 error. And then we also talk about our level of confidence, which is usually 1. Alpha is equals to 1 minus the confidence. So from this alpha, we can be able to say what is our level of confidence. So you can use the critical values, as I've said. You can look at the t distribution, and you can be able, so the t distribution will be a table that will characterize where, you can be able to read that when I have n degrees, when my degrees of freedom is 21, my alpha is this, and my what would be the t, and then you check whether the t that you got is greater or less than the t on the table. So let's see let me come out and see if it will open. Yeah, so this would be your t. It's like, so you have these tables, right? Which, if you are doing these things manually, you can use for yourselves. So you will know that here our n-1 was, it's 21. So the degrees of freedom here, I have to look here. And then I have to look at my 0.05, which is here. I'm doing a two-tail test here. So the t value would be this. And then I have to check whether this value, how does it compare with the one that I computed. So we come back here, the t value was this much, and then this is less than this is more than this. So we can actually reject the null hypothesis. So the null hypothesis was saying that the birth weight is normal. So the data that we've collected says we can reject the null hypothesis. Yeah, I've summarized this, that the negative, the positive, because it's symmetric, right? And then the null hypothesis says the population is equals to 3.5. Larger values are more in support of the alternate hypothesis. So this is what we got from SPSS. So that one, I computed it using I looked at that table, the distribution, but in SPSS, it's going to compute it. It's going to give you the t value here. It's the same as what we computed manually. 30 degrees of freedom, it's n-1. Here now the decision will be based on the p value. So this p value is small, right? Meaning this t is here. Then we can actually reject the null hypothesis. We have small values, not a lot of values that are on the extreme. So we can actually, here we can reject the null hypothesis that says that the average is normal. So if we move on to another test, which is independent sample t-test, I've explained that here we still have a quantitative, and then we have a categorical. So the null hypothesis will be about two groups which are independent. It will say they are the same. It's about their average, right? I've already said that the tests that we look at now are about means, population means. So we are hypothesizing that the means of the two groups are the same, meaning that if, for example, the one who got a treatment, their average is the same as those who didn't get a treatment. So, for example, the test statistic, when we are looking at two groups, it's going to look like this. So you will have the population average, the sample average for group 1 and for group 2, which will be maybe the group that gets the treatment and the one that doesn't get the treatment. And then you can get your pooled variance. Same here. It's going to be a t-distribution. It's characterized by the degrees of freedom. So here, because here we have the sample variance for one group, and for the other group, there are two parameters. So it's the degrees of freedom will be n plus m, which is the size of group 1, the size of group 2 minus 2. And I think we can see again here what happens when the two are the same or close to each other. That's when the null hypothesis is true, the t will be close to 0. So when you have large values of t, they show a deviation from the bigger values of t are showing us deviation from the null hypothesis. So this is an example. Suppose we wanted to compare amount that is spent by customers. So these customers, one group, they get a promotion. It was sent by email. And then the other group, they give them a new promotion. So the company has come up with a promotion, a new advert kind of, and they gave some of their customers the old promotion, and they gave others a new promotion. So you want to compare the amount spent. So you want to check the effect, if the promotion has an effect on the amount spent by the customers. So this is just a screenshot of how the data looks like. And then I think from now on, we will just use the output from SPSS. So our null hypothesis will say the average amount spent by customers who received the standard promotion is the same as the one that was spent by those who received a new. And then the alternate hypothesis is what you want to show, right? To say that the new promotion has an effect on how much customers spent, such that the standard and the amount spent for those who got standard and those who got a new, it's not the same. So this is just a summary. So this is the amount spent from our data. And then this is the amount spent by those. So we do now and check if there's a significant difference. So what I didn't mention is when we have independent samples, one assumption was that the data is symmetric. And then the other assumption is that the two samples, they have equal variances. So it's one assumption there. When it comes to assumptions, you can do your tests. As I say, you use all different pieces of information. So for example, we know when you have large data, we know that you can bank on the central limit theorem to say there will be a symmetry. Yes, but as I've said, you need to also look at the particular variable that you'll be working with. And then what is advisable is you can do your test. And then once you've done the test, you now go back and check and see if what you have is makes sense for under this assumption of symmetry. But the other thing is that these statistical tests, we also say they are robust to deviations from normality. So that you see, this is another piece of information. We know that they are robust to deviations from normality. So it doesn't mean that, so that's why you must plot it, look at it, and consider everything, that I have a large sample and the deviations are not really that bad. And then I can continue and assume symmetry. So it doesn't mean that any small deviation, you use a non-parametric test. There are variables that are very skewed, which it doesn't matter how big the sample is, will be, they will be very skewed. So for those variables, that's where you have to apply. So it's important to know your variables and their behavior. For example, people who work with water quality parameters, some of the variables, you find that, for example, they are constant. You find that you are measuring them, but they don't really fluctuate that much. Those, they will not be normally distributed, right? Yes, and some variables, they are usually transformed. So they know that this particular variable, I can't work with it as it is. I have to transform it before I analyze it. So those things, your understanding of the variables that you are measuring comes into play when you make a decision as to whether, in terms of symmetry, whether you say that you can continue and use a parametric test, or you can say the deviation from symmetry is it's quite extensive. So what I also wanted to mention here is that you have assumptions. So some of the assumptions, you can check them using statistical test. And one such assumption is to test whether the variances are homogeneous or they are the same. So if you look at the results, the left, there is this line here that kind of divides the it divides the results into two. The left where you have the assumption, and the right where it's your results. So what is important is when you are going to test assumptions using a statistical test, the null hypothesis for assumptions, the null hypothesis says that the assumption is met. So for when you test hypothesis for assumptions, like here, we are talking about an assumption about equality of variance. The null hypothesis in this case will say that the variances are equal, or this assumption actually holds. The variances are equal. So here, you don't want to reject it, right? You don't really want to reject it. You are looking for a small p-value. I mean, a high p-value, because you don't want to reject it. The null hypothesis says the variances are equal, meaning the assumption is met. So you don't want to reject it. Like here, you have a high p-value, so you don't reject it. Coming back to what we wanted to do, we wanted to compare. If we look at our p-value here, we're doing a two-sided. We see we have a small p-value, right? And we can see the difference is this much in the range of our confidence interval. And then the p-value is less than 0.05. So we reject the null hypothesis. There is a significant difference between the average amount spent by customers who received a standard promotion insight and those who received a new one. And then we can also have a t-test where we look at two samples, but they are dependent. So when we are looking at two samples and they're dependent, we said it's a dependent sample t-test, or we say it's a paired t-test. The data that we use here for the example is data about credit card, customer's credit card, and their expenditure on different transactions. So you can see the data. You can see the date of birth, the ID, the card type, the month of expenditure where they purchased, and the items. So the type of transaction. So it's classifying whether the transaction was for grocery, retail, entertainment, and so on. And then there is a variable that tells us how much they spent and the amount of the items, the number of items. Then you can see the data is for 2 years, right? And it's also quantified. It's also captured in terms of quarters. So in this example, what we can be interested in is to look at how much the customer spent in 2007 versus 2008. So it's two groups. One is year one, the other group is year two. And it's dependent because it's me as a customer. I'm the same customer. You want to see how much I spent in year one versus in year two. So that would be dependent, and I'll do a petty test. What's important is that with the petty test also, you must just be careful in SPSS that the data has to sit this way, because we want to compare how much you spent in year two here, in year one and in year two. The data has to be in this format. It has to be side by side like this. There is another way. This data didn't come like this. The way it came, the customers were repeated. So meaning here now you see there's one record per customer. This is one customer. And then this is everything about the customer that we wanted. We deleted some things because we just wanted the total for year one, the total for year two. And we were also just looking at groceries. We were only looking, you can see here, the comparison was for groceries. But the data, the way it came, for a person, the data you had, how much they spent, it was going down. If you look at this, it was going down where this person appeared 24 times because it was capturing everything per month. So you had data for the 12 months of 2007, data for the 12 months of 2008, which is the person would appear 24 times. But because we were looking at the total amount, we added the amount they spent for groceries for per year. And then we removed, so that we just have one record that shows that this is how much you spent this year, this is how much you spent. So the variables have to be sitting side by side. The ones that you want to compare, they have to sit side by side like this. As I say, the data, when it came, they were sitting going down on top of each other. We had to change the data, which I think something that is important, because you'll run the analysis and it's not going to get you where you want to go. So this is the summary. So even in this case, we're saying that the difference between the two is 0. So the analysis will be on the differences. What I spent in 2007 and 2008, it's what is going to be analyzed to say the differences, the average differences, they are 0. So this you can analyze actually even also as a one sample, because if you compute the differences, you just have one line of differences, and I can analyze it as one sample. And you can see the results. So here it was analyzed as a petty test. You can look at the p-value here, the two-sided p-value here. It's telling us that there is a significant difference in the amount they spent between the 2 years. So even if you analyze it you take the differences, right? And you make them what you analyze. You check if these differences, they give you 0. You'd still get the same, you get to the same conclusion that we reject the null hypothesis that says the amount spent between the 2 years is the same. Then I'm moving to analysis of variance. So with analysis of variance, I've explained that when we have more than two levels or two population means, even here we're looking for equality of means. We want to know whether the differences between the samples, because I have a sample that got treatment, a sample that got another treatment, and a sample that maybe didn't get a treatment. I want to know if the differences between the samples, are they just due to sampling error, or is it because they differ because of the treatment? Yes. So we use it when we have more than two population means. If you have two population means and you use an Anova, it will simply convert into a t-test. So in terms of the hypothesis, you can see here we have more than two populations. So the mean, depending on how many they are, we are saying they are all equal, right? That's our null hypothesis. And then the alternate hypothesis will say, I have at least a pair that is not equal. So the null hypothesis, the alternate hypothesis doesn't say all of them are not the same, but at least I have one pair. Because remember, if I have three, it's going to be 1 and 2, 1 and 3, and 2 and 3. Those will be the pairs. So at least one of these pairs differ. In terms of the assumptions, we also have homogeneity or equality of variances and the assumption of symmetry. I've already said that even the Anova is robust to deviations from normality. So it can tolerate deviations very well. If as I say, the deviation is very extreme, I use the example of income, then you can transform the data, or you can use a non-parametric approach. So with Anova, we are comparing samples, their variation. If the variation between the samples is larger than the variation within the sample, the means of the different samples will not be equal. And similarly, if the variation between some samples and the variation within samples are approximately the same, there will not be a difference. So whenever we talk variance, sample variance, you must remember this. And we divide by the degree. So whenever we talk sample variance, you must remember this. So this is just a breakdown of what was stated. That if we have three samples, for example, these are the observations. Let's say there's 5 observations, sample 1, sample. You can compute the mean of each sample, right? And then when we look at between sample variation, between sample, we're looking at whether the variation, between the sample, one sample and the next. So it's going to be the mean and how it deviates from the overall mean. And then the second mean, how it deviates, that's between sample. Then we add up, we get our between sample variation. So that's why I'm saying you must remember this, xi minus x bar. It will now depend on what is xi in this case, and then the squaring will come in. This is what is happening here. In this case, xi is the mean for the group, then the x bar is the overall, which we got here. That's between samples. Within samples, I have 3 samples. When I'm looking within, I will look at how each observation deviates from its mean. So that's within. I'm going within the sample and to see how they deviate from their mean. Then I add up to get my within sample variation. And then here I get my between. So between, it's between the samples. As you can see, it's the mean here, the mean here, and the mean here. When we go within, we look at how you deviate from your own mean within this sample. And then we add up for group 1, group 2, group sample 3. So this is what would be used for the analysis of variance. So I spoke about the within and the between a sample variation. So the variation between sample, if it's larger than within, the means of the different sample will not be equal. If they are approximately the same, there will not be a difference. So you can see we have SS between, which is what? This is within. And then we also SS within, which is what I showed you. We use the degrees of freedom. Between, we are familiar with it. Then we can look at K minus 1. And then we can look at within. It's going to be N minus K. Here it's going to be N minus 3 here. Here it's going to be 3 minus 1. And then we have total. So to do our F statistic, we saw the T statistic there. I showed you the formula. Here, what we'll be using will be the F statistic, which is the ratio between the two. And then we can compute our p-value. Yeah. So obviously, if these are the same, if they are close to each other, the F will be smaller. And then if the between is large, this will be bigger, which will it moves more towards saying that the variation, it's largely because of the between, and the between is because you have the groups that received different treatment. Between is group 1, group 2, group 3. I mean, sample 1, sample 2, and they are different. One got a treatment, this one also got another treatment, the other one. So when the F is bigger, it's lying towards saying that the differences are largely because of the treatment. So if we go to an example here, we have an example. It's about employees, and these employees are given a training course for sales. So some employees received the standard training, then another group received standard training plus a hands-on tutorial, and then another group got a standard training plus a technical training. So we want to compare their sales, their score, how they perform. So all of them will be subjected to an assessment after the training, and we're comparing the scores for the different groups to see how they fared. So the null hypothesis will say what the scores for those who got standard training is the same as those who got standard plus technical, and it's the same as those who got standard plus and a hands-on tutorial. That's the null hypothesis. The alternate hypothesis will say at least one of the pairs. So maybe this one and this and 2 are different, or 2 and 3 are different, or all of them are different, but at least there is one pair that is different. This is also the snapshot of the data. So this will be the summary. So how it's summarized, when you see technical, you know it's technical plus standard. If it's a hands-on tutorial, it's a hands-on tutorial plus standard. And then if it's standard, you just receive the standard training, and this is the scores that were recorded. Then when you look at this, we are doing an F here. This is an F. So we said if it's a small f, obviously it will say that the difference, because on top we have the between divided by within. So when the between, which is the between the groups or the samples, the standard sample, technical, hands-on, when it's large, it links towards saying that the differences are as a result of what they received, because the within is smaller, giving us a large F ratio. So that's what we get. And then because we've got 3 groups, we now need to go and check which groups are different. So we can do a post hoc. If we look at our post hoc analysis, it's telling us that standard and technical, they differ significantly from each other. Standard and hands-on also do differ, but we see technical and hands-on don't differ. So the two, they differ significantly from standard, right? And you can look at this key I minus J. It's standard minus J, meaning that the people who received standard, they scored less, on average 9.9 units less. And then the ones who received a standard versus those who received a hands-on tutorial, on average, they scored 15.7 units, significantly less. So you can see that we didn't do t-tests, many t-tests after, to say, let's do a t-test for standard and technical, a t-test for standard and hands-on, a t-test for technical and hands-on. That would inflate our type 1 error, which is our alpha, if we do many t-tests. So that's why it will actually inflate it to 15%. So it's going to increase our type 1, the probability of committing a type 1 error if we do too many, if we do t-tests. That's why we do a post hoc analysis instead of doing, because some people will say, okay, they are different. Now I want to see which ones are different. I can do 3 t-tests, check technical and standard, technical and hands-on, and hands-on and technical. So as I said, that would inflate your type 1 error. So you do the post hoc test because they've been adjusted. So I move on to analysis of variance. So it's when you have Anova, you can extend it to include one or more continuous variable that influence the outcome or the dependent variable. So these are variables that are not really manipulated in the experiment. So these are variables that you are not interested in seeing how they influence the outcome, but you already know that they influence the outcome. And these variables, we say they are covariates. And if we measure these variables, then we can control for their effect because we already know that they influence the outcome. We can add them into the model. Yeah, when we include them, our within group error is going to be reduced, and we eliminate confounding. So confounding is when there are variables that are influencing your outcome that you didn't measure, and you end up attributing your differences that you are seeing, you attribute them to maybe the treatment, whereas there are other variables that are actually influencing their outcome. So when you are aware of such variables, we say you control for them. So if we look at this example, one example is when you're looking at, sometimes you have a treatment and you want to compare 2 treatments. But at the beginning, what you do maybe is you take initial measurements of the people who are going to go into the treatments. And then one group, you give them a treatment, maybe the other one, you don't give them a treatment. And then you want to see whatever, you measure something. In this example, we look at the weight, right? Here, our group is gender in this data set, and we can compare the 2 groups. The interest is in comparing the 2 groups. In this particular instance, we want to compare the 2 groups. So what we do here is we will take the initial weight as a covariate, because we know the initial weight can actually influence the amount of weight loss. So we can adjust for the initial weight so that the weight loss is not because people went in with actually their weight was maybe they actually weighed, they didn't weigh a lot. And so it also shows in the at the end the final weight. So we can account for the initial weight. So this would be the data, the snapshot. So you can see this is the average, and then this is the average for the females. And you see, this is our model. You can see the weight, WGTO is the initial weight. You can see it's significant here. It's got a significant effect on the final weight. And then here we see that gender, there is no difference in the final weight of these people after controlling for the initial weight. And then I want to show you a table. If we don't control for the initial weight, so if we don't control for the initial weight, this would be treated as a t-test, meaning I'm just comparing the final weight for males and females, and I'm not taking into account the initial. That's going to be a t-test. And you can see the results are saying there's a difference between the final weight of males and females. So if I don't account for that initial weight, I will say that there's a difference. But when I account for the initial weight, I see that there is no difference. So that's why it's important to account for the variables that if you can measure them, influences can influence your outcome so that they don't mask your results such that you attribute the differences to something that's actually not really there. I hope you can see it. Then I'm gonna conclude with repeated measures. I didn't do two-way Anova, an example, because in the repeated measure, if you look at here, I have a group and I also have a time. So with repeated measure we're looking at, it's a paired t-test now, but instead of looking at 2 points, I have more than 2 points. So it becomes an Anova because I no longer have two groups, pre and post. Here, for example, you have 3 measurements. Measurements were taken at 3, so I have 3 groups, and it's dependent because they are measured on the same people over time. I hope you can see that it's one person. They were measured here at 3 time points. So here we can look at the results. And the table here will give us the F statistic. If we look at here, so there is also an assumption about the variances. Here it's called sphericity. So if that assumption, it's if it holds, then you will read the first line. So in this case, I am assuming that it holds when I didn't output that first. And then this is what we get. So if we look at time, so time here, it talks about within subjects. So within, it's what is happening within a subject, right? Which is the measurements that are taken at different time points. They are taken within, it's about one subject. We're looking at whether my measurements today and after 2 months and after 6 months, if there is variability within, that's what we are looking at. That would be the time effect. And then we can see that the p-values, they are high. So we can say there is no significant difference in the depression scores. Here, the scores that you see, they are about depression. This is just a hypothetical data set. So which means that the means of the two groups, they do not change. The depression doesn't change over time. Then if we move on, if we look at the interaction, because we've got 2 terms, that's why I say, so this you can also use, obviously using a two-way Anova, but in terms of the interpretation, how you look at when you have 2 terms, the same principles apply to when you have a two-way, a three-way. You don't really want to have 4-way because they become very difficult to unpack as to when you have an interaction, what it means. We've already spoken about the time effect. If you look at the interaction between, so we want to know, when we talk about interaction, we want to know whether the effect is the same for the 2 groups. The time effect, is it the same for the 2 groups? Yeah. When you have 2 factors, you want to know if I have two factors, do they behave the same? So if I have if my two factors is exercise, the other one is diet, and I have different diets and I have different exercise. So for a person, I put you on a diet and I also put you on an exercise plan. We want to know if how you respond, the diet, does it differ depending on the exercise plan, or do we find that it doesn't matter which exercise plan you are on, the diets, they differ? So you want to know if there is you find that maybe the eating plan behaves differently for different exercises. So the response is different. If I'm on this plan, but I'm on this exercise plan, the response is different as to if I'm on the same plan, but on another exercise plan. So that's what we look at when we look at interactions. So here, the interaction is not significant. Then we say the treatment, the effect is the same for both groups, right, over time. So this is the graph of what we were seeing. So group 1, and then I also have group 2. So group 1, they received something. Group 2, they received something different. You can see here that the lines are almost flat, meaning the slope is roughly 0, right? It's like they are constant. So these measurements for the depression scores over time, whether you are on treatment or not on treatment, they are constant, right? Not decreasing, not increasing. So the effect of time, as we saw, is not significant. And we can see they are almost parallel, which means that whether you are on group 1 or on group 2, the time effect is the same. But what we see is that they are far from each other, which means that the treatment effect is significant, because group 1, the average is here. The group 2, the average would be group 2 here. Group 1, the average would be slightly lower. So I want to show you several of this. The data is just manipulated. You can go back, and I think this is the data sets are small. You can reproduce them, type them in SPSS and run the analysis. So here it's just the same data set that has been tweaked, changed some values so that we can see different things. So I'll just go to the graphs. So if we look at this graph, you can see that the lines are close to each other. So we don't expect the group effect to be. So when we talk the group effect, it's going to be between the group, because when we talk group, we have one group that got the treatment, another one didn't get a treatment. They are on the placebo. So the two groups are independent. So when we talk the groups, we talk between. You see, when I discuss the groups, I talk between. Then when we talk about the time, we talk within. So that's important, because the time is within a subject. The time effect is within a subject because it's me who's being observed at different points in time. So that's within. So coming back to the graph again, you can see that they are close to each other. So we don't expect a between effect. So we don't expect the depression scores to be different in those who got treatment than those who didn't get. But we expect a kind of a time effect, because you can see that the scores are actually increasing, the depression scores are actually increasing over time. Here, the slope is not constant. It's not straight lines, flat, but you can see it's a normal straight line that we expect. It's not something constant like we saw with this one. Here, it's constant. So you see, it was this much. Period 2 is the same, so it's constant. It's not shifting. Here, it's also more or less constant. But here you can see it's increasing. It was this much here, It's this much. Both of them are showing us the same trend. The lines are parallel. I hope you know parallel, meaning that we're seeing the same effect. The time effect is the same for this group and for this group, because so the interaction will not be significant, which is what I've captured here. The interaction won't be significant. The time will be significant because you can see that there is an increasing trend. The scores are no longer constant, but they are increasing. You can look at another one. This is another one. So here, if you just look at the graph, you get a sense that they are far apart, group 1 and group 2, meaning maybe the averages, you expect the group effect, the between subject effect to be significant because they are the two lines, there's a gap between them. And then, but in terms of the pattern, we see they are decreasing here, right? Both of them decreasing. They do look like if they were to continue, they would cross somewhere. So they are not really 100% parallel. They are not 100% parallel. So maybe, yeah, here it's like, yeah, in between. You can say maybe you're expecting some interaction to be significant. So that's what the between, it's confirming the group effect is significant, the gap between them. And then the interaction, yeah, is also significant, and the time. So everything here is significant. You could go and do a post hoc. So here you'd go and do a post hoc and now see, because if the interaction is different, it means that there are points where the time effect is significant, and then there are where it's not significant. So here you see when the time is 1, group 1 and group 2, there's a significant difference. So if you just look at it, even though it's giving us that the interaction is significant, it looks like the differences, they are marginal, they are small, because it's, even though it's not parallel, and it said the interaction effect is not, it's significant, but those differences are marginal, such that here we don't really pick them up. Here it's telling us everything is different, meaning it's actually more like the pattern is the same, but you can see it is close to being parallel, but not really parallel. Then the last one that I wanted to show is this one. So just also manipulating that data. So it's also important to just a graph, look at the graphs of what you are analyzing, and you can see here, even if you haven't looked at the actual results there, you start with the graphs, it gives you an idea of what to expect. They are crossing here, right? Meaning we are expecting, they're not parallel. So we expect the interaction to be significant. And then the other one is increasing, the other one is decreasing. So you can see the time effect is not the same for the two groups. Over time, the other one is decreasing, the score, the depression score. Over time for the other one, it's increasing. I wanted to say, yeah, then you can do, for this one, you can do post hoc to see, okay, what is happening. So at time 1, we see that group 1 and group 2, the scores, you can see they are not significantly different from each other, which is this point. So, and then at time 2 and time 3, the two groups are different. So the interaction actually usually gives you something like this. When the interaction is significant, you find that the behavior is not the same across. So group 1 and group 2 don't behave the same in time 1, time 2, and in time 1, they are close to each other. In time 2 and time 3, they are far from each other. They are significantly different from each other. So the time effect is not the same for the two groups. That's why you do an interaction term to check If there is a significant interaction, you now go and see what is happening. But you see at the beginning, these two groups are the same, but over time, the one group, the depression score is decreasing. So the time has a different effect. The time effect for the other group is kind of increasing. So that's what we talk about when we talk about an interaction. When it's significant, it says now the behavior is not the same. So as I said, you can take this and use them for a two-way ANOVA. If I used exercise and a diet plan. So I said you might find that when they are on diet one, if this were diet, they are on diet one and they are on exercise one, we find that the response is the same, the weight loss is the same. But once they are on diet two, they respond differently. Those who are on this exercise plan, they are on the same diet, but they don't respond the same. Those who are on this plan and those who are on this plan, those who are on this is the diet, they are on the same diet, but the exercise plan, they respond differently. So these ones will also be on the same diet, but the different plans, then they respond differently. So there we say, once the interaction term is significant, you no longer analyze the effects of the diet. You no longer analyze the effects of the exercise plan, because you see they respond differently depending on the combinations. So the response is not the same. It depends on the different combinations. Then now you analyze the interaction, which is like this. But if the interaction is not it's not significant, it's when you have this, it's parallel. So they're responding the same way. Those who are on this plan, they are on different exercise plans, but they are responding the same way. They are on this diet, different exercise plans, but they're responding the same way. So it really now you forget the interaction. You just look at the plan and you look at the exercise and you look at the diet, because their response doesn't change depending on I'm here, I'm there. It's you just look at the diet and you look at the plan. That's a two-way analysis, but I'm using this repeated measure because it's got two factors. It's got a within and a between, but with a two-way, they're going to be between both of them, because the people who are on this plan and on this exercise, this diet, this exercise are different. Every group is different. Every combination is different. I'm going to pause here, Samu, and I apologize for going over time.